This video is about heat capacity and possibly about conservation of heat. So, heat capacity is defined in several ways, but the simplest way to think about heat capacity is it is the amount of heat a substance absorbs in order to gain a certain amount of temperature. So the definition we have written here, to get into a specific value for heat capacity, we say how much energy, how much thermal energy, which is the average kinetic energy in the molecules, how much thermal energy needs to be transferred into a substance to increase 1 kilogram of it by 1 degree Celsius. So it depends on several things. The mass of the substance, obviously, the more heat transfer depends on several things. The mass of the substance, so how much of the substance exists that you're trying to heat up. And also, if you've got two substances together and one's hotter than the other and giving the second one heat, the mass of the source also matters. The temperature difference between the two of them makes a difference as well on how heat transfer happens. Usually a bigger temperature difference means a faster temperature change, or heat transfer. So higher temperature difference, faster heat transfer. So that makes a difference as well. We're not going to get into that in this course. And finally, the type of substance, which leads us to that specific heat capacity concept. So specific heat capacity depends on the substance involved. Certain substances will hold more heat than others. Now, we take this forward, we're going to do a calculation based on heat capacity, but let's start with the actual equation. So the equation for heat capacity, the equation for heat transfer into or out of a substance is the heat energy is equal to the mass of the substance times the heat capacity of the substance times how many degrees Celsius it changes in temperature, or Kelvin. And I'll point out, I use delta EH in this course, but in a lot of books they use Q. So Q can also represent the heat of a substance. You'll see that in a lot of chemistry textbooks, and you'll probably see it in a lot of physics textbooks as well. Possibly ours, I can't remember, to be honest. So this is the equation, and really what it comes down to, if you think about this, heat energy, it's an energy, it's measured in joules, or in imperial, it's in calories. This is in kilograms. This is in degrees Celsius. And your heat capacity matches up these values. Now, joules, a joule is equal to kilogram meters squared per second squared, but we're not going to break it down this way when we do heat capacity. All we're going to do is say joules per kilogram degrees Celsius. So that's this part right here on the handout, or on the slide. So heat capacity, the mass of the substance, the heat capacity of the substance, the temperature change, multiply together to tell you how much heat energy has been transferred. And of course, this is an equation, just like any of the other equations we've used, with 4 variables. You can solve for any one of them if you have the other 3. So to illustrate this with an example, we have water, 2.2 kilograms of water, and we want to take it from 20 degrees Celsius to its boiling point, which is 100 degrees Celsius. So your first step, pause the video right now and find the heat capacity of water. Come back. When you have the heat capacity of water, now see if you can work this out without any help from me. Quick pause, try that. All right. So assuming you weren't able to come to the value, and check and make sure you did it the right way, we start with this equation, delta EH equals mc delta T, mass, heat capacity, and change in temperature. Delta T, by the way, is the change in temperature, which means it's the final temperature minus the initial temperature. It's just like change in velocity is the final velocity minus the initial velocity. So this is how we write it. And in this case, it's going to be a final temperature of 100 degrees Celsius, an initial temperature of 20 degrees Celsius. So delta T is going to be 80 degrees. You can check that beforehand. There's the heat capacity of water. I believe the textbook gives you a number like 4.18 times 10 to the power of 3. 4.2 times 10 to the 3 is good enough for now. When you calculate it, you're going to multiply those three values. So you're going to have a mass of 2.2 kilograms. You're going to have a change in temperature at 80 degrees Celsius. And then you're going to have a heat capacity of 4.2 times 10 to the 3, or 4,200. When you multiply those together, you get 740,000 joules. And I want to point out, water has a very high heat capacity, which means it takes a lot of heat to warm water up, and when water cools down, it has to release a lot of heat. That's useful. We'll talk about that in class. That's very useful to life. Okay, so here are 3 practice exercises. Pause the video and give a try for all 3 of these, and I will reveal the answers in a minute. I'll give you a second to check it. Pause the video, calculate, come back, start the video up again, and I'll show you the answers. Okay, so the first one. This is the mass. We want delta T. And we're given EH. And you will have to find C of mercury. So if you didn't get this far, pause it now and try. And of course, you're solving for delta T, so it's going to be delta T equals EH, or delta EH over MC. And that will give you a temperature change of 234 degrees Celsius. So 234 degrees Celsius. Now, if you had trouble with it, if you didn't get the same answer, stop and try the next one before you look at the answer. When you get here, you're given delta EH. You can find your mass, your heat capacity of copper. You have a delta T, and you're being asked for the mass of copper. So calculate that out. Your answer is 16 kilograms. And the last one, again, same drill. Pause. Try this again if you're not comfortable. And here we go. 15 to 40 degrees Celsius. Water from 15 to 40 degrees Celsius. 1.5 kilograms. 157,000 joules. Now take a quick look at the difference in heat energy there. 25 degrees isn't a very big temperature change, but it's a huge amount of energy for it. Finally, if we take the same amount of water, or same amount of mass, but make it aluminum instead of water, how much energy does that take? 34,000. So water is 4.5, 5 times as much energy as aluminum. So water has a very high heat capacity. All right, moving on. That is the end of the portion on heat capacity. Let's check our time here. 8 minutes. I'm going to stop this, and you can watch the separate video on conservation of heat.